Hello, and welcome back to the live stream. So, in the last couple of episodes, we worked on arrays, and where we only tested single-dimensional arrays. In principle, everything is defined recursively. So, multi-dimensional arrays like the one here should just work. In practice, the compiler crashes, which obviously isn't ideal. So, let's see what's going on here. Let me enable sanitizers. And let's see. Having to recompile everything. Well, linking takes a long time. Okay. Member access with a null pointer. Okay. Of type. So this one is null. Because this one returns a null pointer for an array type. Okay. So what the hell are we doing? We want to do an addition operation. We want to figure out the type of the pointer. Okay, what are we doing? So it has to do something with the axis, and we're adding like the offset somewhere. And this sort of assumes that we're having a pointer. So we should have a pointy type, right? But when we actually then get the type, we're returning a null pointer. So we're hitting one of those cases. Huh. So what happens? So this one obviously doesn't compile. Right. Allows of sign is not a modifier L value. We can't do an implicit conversion. And a bit annoying that the error allocation is correct. It's just because of this nonsense here, the error is misaligned. So it's still at the correct place. Okay. So that one works, but only if we have a nested one. Okay, so I'd like to see the AST that we're generating, but we're crashing, so we need to do something here. Do I have an assert? I have an assert. Pointy type. It's not null. Maybe then we get a printout. No, we can't. Why are we not printing? Let me figure out. Go to the entire code stack. Oh, I know why we're not printing. We're printing outward. So, what's the best way to debug this issue? I think it's just if we have a null pointer, let's just patch around that. By doing that. Just so we can get to the point where we print the EST at the end. Okay, so this is what I wanted to do. So we've got the assignment expression, whose left-hand side left-hand side is a nested derivative. So we've got the identifier expression, which has type 1 to signed in 64, which we're decaying to a pointer to an array of 2, which makes sense because arrays always decay to pointers. We're then doing an offset with the integer constant 0 on the other end. The result then gets a pointer to an array to signed in 64, which we're dereferencing and decaying to get a pointer to signed in 64. Yeah, sort of makes sense. But we're then doing the offset. So why? I'm presuming we are in the second add, which failed, or in the first one. So let's see. So the type, do I've got functions? Yeah, I've got dump type. So let's just call dump type. And get the question. Okay, so let's flush you out. So the type is a pointer to assigned in 64, which then, okay. So we've got a pointer to assigned in 64. And we want the type of the, right, so it does make sense. So we're having a pointer type. We're getting the pointee, and we're asking for its layout so we can do the correct offset. But this one doesn't work, because for arrays we don't have a native type, we're only having a layout. So the correct fix at this point is we don't want codegen type, we want codegen layout. And then we're already having the size here. And we are doing the same thing right here. So arrays are first class type, so we don't have a type for them, we only have a layout. And so when we do the offset manipulation, we cannot access the type, only its layout. Okay. So now the example compiles again. This sets the first element to 0. So we've got, we're allocating 16 bytes, which is enough for 2 because our array has 2 elements, so that's correct. And then we are doing like 2 address offsets with 0. So let's print out 0, 0. So that is 1, which we just set. And this should also be the one when we cast it. So the first element is the one that we're setting, which is correct. Let's set the second one. So we've got an array like, yeah, that one, right? Let's set that to 2. Okay, that doesn't look great. Oh, we've got a memo leak, that's fine. But we got a panic for the invalid address. Probably because we are having the dimensions mixed up. So we are having, so the first offset, what we're doing is we've got an array of 1, we've got an array of 1 of an array of 2 signed in 64, right? That seems correct. So we've got an array of 1. Oh wait, is it? Oh, I was confused by those things. So this is an array that contains, I believe we have them flipped. Oh, no, we don't. So when we do one axis, we're getting an, okay. Right, so this is the index, yes. So we're indexing those correctly. So the inner array has 2 elements and the outer array has 1. And then we're getting the type. We've got the inner array has, yeah, the inner array has 2 elements. And the outer array has 1. So the type is correct. We've got 1, then 2, then signed in 64. And on access, we are accessing it the other way around. Because on access, the inner array is stripping out the, so the first index is stripping away the other dimension. Right? So here we've got the first offset with integer constant 1, which operates on the outer array instead of the inner one. So we have to swap that. That seems a bit weird. Subscripting. Subscripting if E is an n-dimensional array of dimensions it's converted to a pointer, right? We're stripping the leftmost. Example, here is an array of 3 times 5 objects. X is an array of 3 element objects, each of which is an array of 5 objects of type. Oh, so the type is the other way around. Right. So X is an array of 3 of 5 of int. So here we've got array is an array of 2 of 1 of int. Array of 2. Let me use the exact same example so I can get the 3 of 5. So 3 of 5 of int. So X is an array of 3 elements, each of which is an array of 5, which is of int, right? And this is the other way around. So we are passing them the wrong way. So array is supposed to be the other way around. So somewhere where we're passing the declarators, we're passing an array declarator, which is a postfix declarator. Right, so this is a postfix operation. Which is here we're creating the array. But this processes the inner one first and not the outer one. So we get our array and we pass the 3 first. Okay. So we pass the 3 first, so that's the inner type, but it should be the outer type. Man, how do we fix that? I have an idea how we can best fix that. So we've got a function get type or something, get type. Yeah, so that gets a declarator and gets its type. And for an array declarator, we are getting the element type and then creating an array. We sort of need to swap them around. All right. So we need to pass the type down from above. So we've got. So we create the first array using our dimension. And then we're asking the second one. Right. So currently what we're doing is we are, okay, so we're creating an outer array first. By cloning the decl type. And then we're passing that one in types to the child with the outer array. So in the opposite order, so we get the correct one. This means that the element type is actually the decl type. We need to check for that. And then we need to do that. And now we've got an array of 3 elements of 5 of int, which is what this one's supposed to be. Here's an array of X is an array of 3 elements, each of which is an array of 5 objects of int. So array is an array of 3 elements, each of which is an array of 5 elements of int. So that's now the correct order. So let me add a comment here. We need to process array declarators from the inside out So we first add our declarator, then process towards the child. So in the opposite order, so we can get the correct dimension. And now we should be able to have this one. So this is now an array of 2 of 1 of int. So this one all works. And if we interpret it linearly, we've got 1, 2. Yes, we've got 1, 2. So we're respecting the array layout. If we're now having an array of 2 of 2, and we can add the same ones here, 3, 4, 2, 3. We're getting, yes, this is correct, I think, right? Because they are stored in, is the layout specified? But like the inner arrays, like the inner index varies first, I believe. I always get this one mixed up, but I think that's correct. Let me actually check this one. Int I. Printf by using a real compiler 1324, right? So we're having the same layout. 1324. Okay, so let's turn that into text. Array like so. And let's set them less confusingly. And let's also get the vary the dimensions so we can test that. 5 and 6. And then we get a pointer to the first array element. Pointer 0, 1. Pointer 1 is 2. Pointer 2, 3, 4, 5. And 6. So that's multidimensional arrays. Okay. This one, sure, why not? This one not. This one not. This one not. This one. Switch order for multidimensional array types. The array dimensions were wrong. Fix array offset. And I don't need that flush anymore. Okay. Now the second part is we can have arrays. Arrays can be initialized. 1, 2, 3, 4. That one just worked out of the box. Great. So let's copy that test. One, 2, 3, 4. And let's keep the last two at 0. 0, 0. That one passes. Add test for multi-dimensional array initialization. And finally, we can leave one dimension, like we don't need one of those dimensions, and I don't remember which one. That one? Right, so we definitely need one of those. Right, so we can leave them the outer ones. Can we also do that? Well, we can. I wasn't expecting that to work. And what if we're having like a 3-dimensional array? Can I then leave multiple ones? All right, so I can only omit one. Right. And now the initializers are messed up. So this is an array of. So it originally was an array of 2 of 1. So this is an array. So each like that, right? That one still has 4 elements, right? Okay. So let's add a final test for that. Cannot do an implicit. All right, we need an extra here, and here we go. Can I do that? Apparently not. Okay. Great. Add test for incomplete multi-dimensional array type. Okay. With that, we're done with arrays. Let's move on to strings. So more arrays. So the first thing is we need a new type, char. Because the fun fact about char, char is a bit of a weird type, where we have types. There are 5 standard signed integer types: signed char, short int, long int, long int. Then we are having, for each of the signed ones, and corresponding unsigned ones. But notably that it talks about like a signed char and a plain char. So unlike everything else, where like int is the same as signed int, char is not the same thing as signed char. Where do we specify char? Right. Yeah, essentially like a char is large enough to store any character. The basic ones are non-negative and the other ones are implementation defined. So essentially the signedness of char is implementation defined. This means that even though we're already having like signed char and unsigned char, we still need a separate type for char. So with an implementation defined signedness, and we're making the only correct choice of unsigned character type char, right? Because why would it be signed? So there is a bunch of code where we're creating the built-in types. Somewhere in the type specifier code, there's a big mess. Where do we use the type? Decal specifier. Here we go. No, that's not the production decal specifier. You? Right. This one. So there are a bunch of specifiers you can pass in front of a type, in front of a declaration, like char or signed or extern or register. And then we've got this messy function that tries to look at all the specifiers that we have and figure out which is the correct combination of base type. And here we go. When the decal specifier is char, the base type is plain char. Right. So that's the base type. And then, depending on the base type, and if you didn't have one, like if you just have signed, that just means int, like signed x means signed int x. So the default is always int. And so we've got a new base type char. So instead of signed int 8, we've got the base type char. It cannot be combined with short. If it's signed, we're creating a signed int. If it's unsigned, so if signed has value and is okay. So if we don't have it, so if we are not having a signed specifier, if we're having neither signed or unsigned in combination with char, then we return plain char. Otherwise, if we have signed, then it's signed char, otherwise it's unsigned char. So let's, right, that's the logic, I think. So if we're having signed, we're setting is signed to true. And if we're having unsigned, we're setting is signed to false. Yes. And I believe that should be enough here. So now, if we are parsing char x, x is now char and not signed char. Of course, we're getting now a bunch of errors because I've added new stuff to an enum. So make unsigned. Is that well defined for char? Can I do make unsigned char? Not actually sure. Like, I'm guessing, like I'm curious what the C++ type def does, because that's sort of what this function is modeled after, where they use that. Right, we do usual arithmetic conversions, and we want to convert the type to an unsigned one. I don't think this case is too important, but in other case, let's say that we may, when we make, do we have a make signed? We don't have a make signed. So, okay, let's see what the actual algorithm is. So the usual arithmetic conversions. Right here. A bunch of cases, integer promotions. Right, so we do integer promotion, and integer promotion should get rid of char, because integer promotion promotes it to int. Pretty sure. Right, so we're doing integer promotion, so we don't actually need, like, we don't need the behavior of this type. Is it like an, that's interesting, like, is char a signed integer type? Ah, man, a bunch of questions that you never really want. Like, why would you ask yourself that? Okay, so let's say we don't say that is not allowed. Okay. Is it assigned? Well, first of all, it's unsigned in our implementation. It's definitely not assigned. But is it an unsigned int? Like, I'm guessing yes. I mean, it's not a signed integer type, and it's neither a unsigned integer type. Let's say it's neither and see what hell breaks. Char. So char is neither, yeah, it's not an integer, right? Is it in C++? It is in C++. According to the type trader, at least. Okay. So let's say it's not an integer, and then we just see what happens. Oh. Right, they definitely, it has to be an integer, because they do, like, you can do arithmetic on them. So let's say it is an unsigned integer of the same rank as the other ones. So essentially we're dealing it, we're treating it as an unsigned integer. Okay. Let's see what else. All right, we want to print it. That's easy. Char. And then we want to get layout out of it, and we are treating it as a uint 8 for the purposes of assembly. So during assembly, it's a uint 8. Right, do integer promotion. And let's say it promotes to a signed in 64. Because it definitely, like, all values can fit in the signed in 64. because our integer type is 64 bits, integer promotion like promotes everything to 64 bits. Okay, so let's see what that does with our example. Why do you need to recompile? You just ran the tests. Yeah, that's probably not a bug. Okay. Oh, right. If we don't have assignedness, then we want to return char. Compiling with sanitizer takes so long, I should switch the build mode. Let me do that right now. Not release, that takes even longer. Debug. So, X has type char, and we're reserving 8 bytes for it. Okay, let's initialize u to 65. Let's also create u, and also create u, just so we can see what difference, if any, that makes. Okay. Yeah, right, now to recompile. Okay. Why do we have a global? Who created you? Why do we have 17? Oh, is it? Oh, I think no, I have no idea. Wait, what the hell are we doing? Oh, we're doing overflow checks. That's what the global is for. Okay, but anyways, that 0.65. So we've got the global, this is a string literal. This says something like, what, 69? Oh, that is hex. I don't know what 69 in hex. It probably says something about integer overflow or something. Right here we're doing, like we're doing some weird stuff in line 4. All right, because signed integer overflow is undefined behavior, so we're panicking if that's the case. So if this is something like 130, we're getting a panic integer overflow. Right. So this is what all this stuff is doing. Although I'm not sure why we are... Oh, right. Interesting. So it has been partially constant folded. So 82 is 130. And then we are pushing v1 because we're definitely having an overflow. And then we're panicking if 1 is true. So we're unconditionally panicking. And in the previous case where we have 127, constant folding pushed a 0, so we're never panicking. But it wasn't smart enough to then elide the global address and the panic if as well. So this is still left here. So we're doing a bit of constant folding, but not enough to completely eliminate the overflow check. But anyways, so that part seems to work. So we now got 3 distinct types, char, assigned and 8, and u and 8. And then we can manipulate them as usual. So let's commit that. Add char type. So the interesting thing is, of course, we want character literals, right? So we want to say A instead of 65. So let's handle those. We've got an expression for that, I'm assuming, like lexical element, constant, character constant. We've got an encoding prefix, let's not worry about that, and always use UTF-8. And then a C-char sequence, which is a sequence of chars, C-chars, which is any member of the source character set, whatever that means, except for those. And then we've got escape sequences, a bunch of them, yada, yada, yada. Okay. So what I want to do, and it's also like this is a sequence, and so you can put like multiple ones and initialize those to a single one. Yeah, a sequence of one or more characters. And then we got escape, constraints, semantics, and of course it has type int, because why not? The value of more than one character is implementation defined. Okay, so contains a single character. Let's just implement the intuitive semantics. So we've got summary, we've got expression. Primary expression, we've got non-pointer constant, integer constant. So let's add a new constant expression. What's it called? Character constant. Character constant. Character constant expression. So it's a sequence of stuff with an optional escape sequence. Right. So single quoted sequence of chars, which is members of the source character set. And the source character set contains ASCII characters, except for Newland. Oh, and the other. What's the source character set? Universal character. No, source character set. Do I have a thing here? Source st O is for T, right? Yes. Source character set. Source character set. 18. Environmental content. Right. And the character members of members of the source character set. 26 uppercase letters, lowercase letters. Okay, so ASCII except for control. Yeah, let's just say that. Hang on, how do I actually then do UTF-8? I'm guessing like they don't fit in a char anyway. Man, this is messy. Character constant. Char sequence. Any member of the source character set. String literals. Any member of the source character set. Oh, right. Like, so, okay, so we've got like source character set is implementation defined. So let's just, okay. Let's make it Unicode. So this is a Unicode character that isn't a control type. Right. And then we've got escape sequences. We've got octal, hexadecimal. Simple, octal. Okay. So escape. That's defined here because we're reusing that for string level. So escape sequence. So they start with a backslash. And then we've got symbols. Right. So simple escape sequence. This is a symbol table that creates characters, and we're mapping those ones. So you gets mapped to yourself. You get mapped to yourself. Question mark for some reason gets mapped to itself. Then we're having the backslash, which also maps to itself. And then we've got A, B, F, N, R, T, V. And those ones map to whatever they're supposed to be mapping. A, B, A, B, F, N, R, T, V. F, A, B, F. N, R, T, B. Okay, so you allow any basic symbol from the simple escape sequence. Then we've got octal escape sequence, which consists of up to 3 octal digits. Let's ignore those. Let's just do that for now and extend it later. So we've got single quoted with an optional escape sequence. And we want to convert those to a string in UTF-8. Okay, so that's a character constant expression. And Lexi will now parse the UTF-8 for us and will convert that into a string. We can now add those to the expression thing. Right, so, and add a new callback for those. So, when we've got, so somewhere we are presumably creating integer expressions or something. Are we doing it directly here? Okay, so let's also do that. So let's convert those to a string. And then we return, because this is an integer, right? Semantically. This is an integer character constant. So we can just treat that as an integer literal. That has been funnily written. So callback. Develop integer constant expression. Compiler state state. I'm guessing I need a position here, and then we're getting okay. So now we want to create the value. So the standard says something about, I remember reading that. The numerical value is the one as the integer, or whatever. And the value of more than one character is implementation defined. And if it contains a single character, then whose value is that of the char. So since more is implementation defined, and I'm assuming the maximum number is okay, then what we can just say is the value is just the first character. And if we happen to have more than that, implementation defined, we can just ignore them. So even though we're getting like potentially an entire string in there, which is like allowed for some reason, we just take the first character as the value of the character constant. So the value is the first one of the string, and then we're returning type and value, right? So state as create of integer constant expression at the position state as create built-in type int64 because of course character constant is the 64-bit integer and that value, right? And that should be that. And because we are reusing mechanism for integer constants, everything should just work. And look at that. We've got a char x initialized by the integer constant expression 65, which is kind of true. And as I said, because this is allowed, and implementation defined just the first value, right? C is such a weird language. Okay, so we've got the basic escape sequences like so. 10 seems correct. So that part works. Let's then add the more fancy escape sequences. So the fancy escape sequences are a universal character name. I know right here is U followed by 4 hex digits or uppercase U followed by 8 hex digits. That rule code point ID 4. So if we're having a lowercase u, then 4. And if we're having an uppercase u, then 8. And Clang format doesn't like variable templates followed by the shift operator. So now we should be able to do something like 0, 0, AB, which then gets truncated down. Yeah, but like that's fine. It's not too large because it's an unsigned. But anyways, so that's that. Then we've got the hex ones, which is x followed by hexadecimal. This is defined weirdly. So essentially, this is x followed by as many hexadecimal digits as possible, which is nice. So like you can do something like A, B, C, D, E, F, right? And that's whole one number. There's probably a constraint in there. Hexadecimal digits, numerical value specifies the value. Yeah, longest sequence. Constraints shall be in the range, right, of unsigned char. So even though this is always an error, right, this isn't interpreted as that, which is nice. Man, why is this language the way it is? Okay, so let's add those. If we're having an x, only a lowercase x, not an uppercase x. Only a lowercase one, sure. Followed by an integer, unsigned char in hexadecimal. Right, which gives you an integer overflow. And I'm curious the way this is handled. This is 187. 187. So this is handled literally as a byte and not interpreted as a Unicode code point, because then this would be a different number. So yeah, that one, and then the octal ones is just the same thing, but a sequence. Okay. So why a hexadecimal sequence like specified to be as long as possible, but octal escape sequence are at most 3, right? What's the point of that? What, right? So each is the longest sequence that can constitute the escape sequence. Well, no, it isn't. It's only 3 octals. It isn't the longest sequence. Okay, whatever. Let's make it the longest sequence because that's actually easier. And just says that if we are having something that is an octal digit, then we're parsing an unsigned char in octal. And now we can also allow /0 because that is an octal sequence. There isn't actually an escape sequence for / and 0 in C. It's defined via the octal sequence. So you're constantly using. So that's 0, unsurprisingly, and then octal 12 should be what, 10? Yeah, that's 10. And I couldn't, so like, is that now, like, we interpret this as a 3-digit number, but like the grammar says we're only looking the first 3 digits, so we ignore that one, but then this says that it's the maximal longest sequence. So I don't know. But who cares? Okay. So it adds escape. No, character literals, right? This all we added. Add character constant. Okay, so now we've got char and character constant. Next up is strings. So strings actually come in 2 forms. So we can do that. And we can do that. And in both cases, they do entirely different things, right? Here we're creating essentially a global constant containing A, B, C, and 0. And here we are doing essentially that. So yeah. Let's see what the standard has to say about that. So we've got the string literal, which essentially, like, grammar-wise, it's the same thing as the one above, just with different quotes. Then we've got translation phase bullshit. So that's that. But then I'm curious about how it's treated in the expressions. Right, so we've got a string literal as a primary expression, and then I'm guessing a string literal separately as an initializer or something. Or maybe not. So where this one, like, because string literals appeared in that there are L values and whatnot. Where do we got initializers? Right here. Yeah, no. So something about initialization. An array of, right, maybe initialized by a character string literal, which translates that into the corresponding byte thingy. So, and then somewhere else it probably specifies that string literals are L values and whatnot. An L value is an expression that potentially designates an offset. I'm assuming it says it somewhere. Storage duration of objects, maybe? No. I mean, like, is it not specified in, like, the string literal? Then used to, yeah, right here. Is then used to initialize an array of static storage duration and length just sufficient to contain the sequence. Right. So, Let's parse it, add it to the AST, and worry about that later. I believe that's the do it one step at a time. So we've got the null pointer constant expression and the integer constant expression. Let's add the string constant expression. It's not a constant expression. It's a string literal, right? So string literal expression, quiet basic node kind string literal expression containing a string. Explicit string literal expression. It has a type, which I'm guessing is array of char. Let me get a move macro from somewhere. Alright, so then I need to include string. Let's actually, let's intern those. Because why not? So let's not use string, let's use, we've got symbols in there. S symbol. Value. S symbol value. That's all. So that's essentially an intern string, and that way we don't have to do dynamic memory allocation and stuff. Integer constant string literal expression. Okay. And let's just follow the compilation errors for a while. All right, not handled in string. String literal expression, string literal expression. Oh, that's the same one. Okay, and then we've got, like, I'm assuming a bunch of cases that visits expressions that we need to adjust. So it is an L value. Now it has kind of string literal expression. Then we return true. Now, I know that it must not be modified, but it is not const qualified, which begs the question, is it a modifiable L value? Like, it's undefined behavior to modify it, but that hasn't stopped, never stopped anybody. Modify L value is an L value that does not have array type. I mean, it has array type, I'm assuming. Right? So then used to initialize an array. Yeah, it's an array. Yeah, I'm guessing like it has type array of string, right? Array of char. I'm pretty sure. Yeah, let's just treat it as an array of char. It has an L value with address, whatever the hell that means. Oh, right. Is it an L value that has an address? Yes, it is. Because not all L values actually have an address, because register is a thing. So, but this one is, it also is one with static storage duration. where we're using that. If we're getting the address of a thing. Okay. Not pointer constant is not a named constant, not an arithmetic constant expression. But we're doing a visit all, so we need to add that. So return ports. It's not an integer constant expression. It's not an address constant. Let's just say it isn't. If you have no idea what that means. It's not an initializer. This is about decals. This is about decals. This is about toString. Okay. And finally, we need to handle that in CodeGen. Type call built-in. So we want to CodeGen it as an L value, which means that const c string literal expression. The CodeGen is as an L value. We're building a global static array initialized to that thing. So Adam build string literal into our builder. Expression value c string context ast symbols. Part of the context. Do we even have the context? So we've got the. I don't actually have the AST. Okay, you know what? I'm too lazy to pass it all in, because then I need to adjust 1000 constructor calls. Let's just say string literal. Let's be sneaky. Store the C string directly. And worry about lifetime. So we create a string literal, and then we want to get this address, which is as simple as that. Get the address of the global that contains the string literal. Now as an R value, that essentially means to dereference stuff. Or something. Right? A valid expression as an R value. So this one pushes the address. Right, since the identifier expression behaves the same way, let's just copy it and say that if you have an integer constant, we are getting that thing. I believe since we need to insert like a decay expression, which does the actual dereference, pushing the address here is correct. So this one also pushes the address onto the stack. Yeah. Let's just add it to the compiler and see what happens. So the compiler. We've got the character constant expression. We also now got the string literal expression. The rule is quite essentially the same. We just need to change u to quoted. And then add here. So the value is state as symbols, intern string.data string.length dot cstring state as symbols. Okay, so now we've got the value. The type is an array of char. So state as types build type format creator auto element type creator create built-in type Seed built-in type char, array of char. Seed array type, element type, string.length +1 because of the null terminator. And then we're creating a string literal expression with type and value. Okay. Add a comma here. And then we just need to add you to the parser. Right here. Here's a string literal expression. Right. And const string equal abc. Let's see what happens. Cannot initialize. Oh, I know exactly what this error means. String literal expression. Let's try that again. Okay, so we've got a variable ticket string that is created by, oh, we are not actually printing the string literal, but we're decaying it to a char, casting it to a const char, using it to initialize the string, and we do have a global here, and that has 4 characters, which appears to be correct. And I think 60 is, yeah, that appears to be ABC. Let's actually print it. Print it in the AST, I mean. So we've got the built-in expression type content right here. Const string literal expression printf print something like that. And then we dump the type. So we've got ABC of type array of 4 chars. Let's actually print it in the program. 1, 2, 3. 97, 98, 99. Yeah, that should be ABC. What happens if we try to modify it? Alias of sign is not a modifiable L value. Sure. What happens now? We're getting a panic on an invalid address. Great. Well, I mean, not great. Like, why is the type not const qualified? But okay. So that actually is string literals, right? I should be able to do stuff like print hello 1 or something. Yeah. So great. Should be able to take its address. Pointer. This looks so wrong. Cannot do implicit conversion in assignment. All right, because this is a pointer. This is a pointer to an array of 4 chars. Wow, I honestly wasn't expecting that this one parses correctly the first time. Okay, so that's string literals. Add string literals. Yeah, add string literals. Now we need to adjust the one thing that doesn't work. We can also do that. And this is a shorthand for A, B, C, 0. But we're not handling that one. invalid use of incomplete object type, cannot initialize array from expression. So we're not handling U. So let's try to make that one work first. Cannot initialize array from expression. Cannot initialize array from expression right here. So we've got an expression in it for an array. Right. So we cannot unconditionally create the arrow only if it's not a string literal. So if auto string literal, let's just say string, now try cast cloud string literal expression init expression. Now what does the standard say? Somewhere it said about like constraint about the character type. I'm hoping it's here under initialization. I read that today. An element type compatible. Compatible with qualified or unqualified. What's compatible? I mean, like I know what's compatible. There's the whole clause somewhere above about compatible types and whatever. Okay. So if we're having a string literal, string and the zero let's just say is like char element type sudo also allow types compatible with char. So if that's the case, then we allow this initialization. And what do? Oh, we're just verifying it, right? So we verify it by returning, I guess. Okay, so init function is char, is integer, is char. Zero is char. Return built-in kind zero, built-in type char. Okay, so if we're having a char, then we are compatible. Yeah. So we should now allow that in the compiler and probably crash during codegen. This is type kind, type kind. Kind is the kind of node, so kind would be built in type. Cannot initialize array. Really? Still. All right, because this is probably... It's probably the type is not a string literal, it's a decay expression of a string literal. Or something. Yeah, it's great to read, not valid. I'm pretty sure that's the case. So let's just say we've got the correct check here and figure out the case where we're triggering that this is not valid C code. Because our definition of valid C code just changed. Ah, right here, expression in upon array, right. Of an array right here. So let's just do nothing for now, just so we can get the AST. We need to do something here. So it's like the address is on top of the stack and we need to get rid of it. Okay, so variable decal, it's initialized by an expression in it, which we are not... Wait, what? We've got an empty expression in it? Why are we not printing that? I'm guessing. Oh, because we don't have a. We're supposed to print something at this point. Because we're having a child or whatever. Array in. What was the RMS? Here we are. Are we, in general, not printing the array init expression? Or is this a different bug? Yeah, here we're printing it. But why are we not printing it here? Okay, so verify does something. Where do we call that? Right, we just verify it. Why is it not part of the... Okay, so let's figure out what exactly is going on here. We're supposed to be called with the init, whose expression should be a string literal expression. Of course, this is absolutely unreadable in the debugger. Oh, it is a decay expression. But why aren't we printing anything? Okay. So if we're having a decay expression, try cast seal of decay expression of that expression, which in turn is a string literal, which in turn is a char type. Then we can no? Oh, I need to actually use decay here. So if you're a decay expression of a string literal of char type, then we can, no? Okay. So we're right here. No, but what are we then? Oh, because the decay expression isn't a string literal, the child of the decay expression is okay. So now we should be, but we're still not printing anything. Why are we not printing anything? That is so weird. Like, okay. Let's just implement CodeGen and I'll look into that off camera. So we've got a string literal. If we reach this point, then we know that this is a string literal. We know that this is a string literal. So what we essentially want to do is we want to memcopy that string literal into our array. And that seems good. So let's do that. For that, we first need to get the string literal. So string literal, we cast you to a string literal expression, decay expression, init expression, child. Then we get the string literal. Build string literal, builder string literal value. So now we got our string. And now we want to mem copy u over. So memory copy. The parameters are destination is already a stack, so we just need the source and the size. So int global address of our string. And let's just make it the size of the array for now, and we need to adjust that. So this should then initialize our array. I'm still so confused, but it's not printing. String 0, string 1, string 2, and string 4. Right? That appears to be an actual error. So if the size doesn't match, no, that's fine. But if we do that, okay, apparently both cases are fine. So so let's do the following. So we get the string length. And then we copy if string length kleiner array size elem layout dot size. So if we're having more in the array than the string, we are only copying over the string. Otherwise, we are copying the entire array. Like so. Why are you not complaining? How many characters are we creating? 8. Why are we creating 8? Oh, right, because this gets rounded up. Right, so we can't create things smaller than 8 bytes, so this isn't a workflow. But in the opposite case, where we're having more, yeah, this is fine, because it's actually getting mem set to 0 at some point. But we should probably do that ourselves, but I'm just adding a to-do because the stream's getting long. To do mem set rest to 0. But yeah, I'm still like really confused why it's not printing. Like I have no idea what's going on here. But that's a problem for later time. Thanks for everybody who stopped by. Did a lot done. We added multidimensional arrays, chars, and string literals. And until next time, we will start calling libc functions from our interpreter. See you then.